I'm working through the test to review problems, and you can watch the recording. So the first question is draw the structure of the following, and first one is benzyl chloride. It is a benzene ring with a CH2 group and then a chloride. Okay, so if you recall, this is my benzyl position. The carbon over here is the benzyl position. Okay, so benzyl chloride would be a chloride attached to the benzyl position. Then the next one was orthochlorophenol. Recall, the ortho position is the 1 and 2 position. So you have your phenol, which is benzene ring with an OH, and then in the ortho position you have a chloro. The next one is a cyclohexyl vinyl ether. So cyclohexyl is this group, and then it's a vinyl, which means you have a carbon-carbon double bond. So that's the answer for this. The next one is rank the acidity of the following molecules. The way is that 1 is the most acidic and 3 is the least acidic. So the most acidic one would be our phenol, and the least acidic is the methylamine. Okay. So we had talked about in class about how to rank molecules in their increasing or decreasing order of their acidity. Here phenol is more acidic because its conjugate base, which is this one, the phenoxide ion, is stabilized by resonance. Okay. Stabilized by resonance. And if you can draw multiple resonance structures for this, where I will draw just one of them here, where you make a double bond to the oxygen, and the lone pair of electrons come over here. So you have the phenoxide ion changing into this structure now, and then you can draw multiple structures from here where you move the electron pair on all over on the ring. Okay, that's the reason phenol is the most acidic, because it's stability of the conjugate base. Now between these two, it's like oxygen is more electronegative than nitrogen, so the proton can be given off more easily in this case than in the amine case. Okay, amines are more basic. They're able to donate the pair of electrons that are in the nitrogen. Okay, the next one is complete the following reactions. The first one looks like a ketone with a reducing agent like sodium borohydride. So here the product would be a reduction product, and alcohols are the products of reductions of ketones, right? So this is my structure. Let me add another reaction here, and that would be, say for example, if you had an alcohol and you were treating it with sodium hydroxide, which is a strong base. Okay, this is a strong base. So the product of this would be an alkoxide ion, because the hydroxide of this is going to act as a strong base and remove this proton from here, and you get a alkoxide ion, and then Na plus over here. Okay? And then your other product will be water. So this is an acid-base reaction where alcohol is acting as a acid. Okay. The next one is we have two OH groups, and then PCC is my oxidizing agent. But remember, PCC is a mild oxidizing agent. Mild oxidizing. So the result would be that only your primary alcohol would be oxidized, and the secondary alcohol will remain intact. So we had 1, 2, 3, 4, 1, 2, 3, 4. So you have you're changing this into an aldehyde. Okay. And the next one is a Williamson's ether synthesis. It's a Williamson's ether synthesis, and if you look at the ingredients of it, we have an alcohol, a base, and an alkyl halide. Okay, so the first step would be where the hydride removes the proton and puts the electrons over here. Okay, you don't have to show mechanisms in these reactions, but you can see that that SN2 reaction can work here, and you need to only write the products in the box. Okay, but I can show you the mechanism here just in case you would like to know. So this acts as a nucleophile, and in the next step we have this CH3, CH2I, where now this nucleophile attacks at this point, iodide leaves, and your product would be where you still have the H, and then we have changed the chirality. If you look at the chirality has changed, then you have the we have formed an ether. Okay. Let me redraw this. We have formed the ether. Oh, actually the chirality does not change here because it is the attack is happening at the oxygen atom and not at the carbon atom. Okay, so you keep the chirality the same as in your starting material. Okay. All right. Let's look at the next problem. We again are continuing with filling up the blank boxes. And here the reaction is asking for one of the reagents. Here if you look, we have an alcohol, we have a sodium hydride which will remove this, and then we again get an alkoxide. But here to form the product, what kind of alkyl halide you will use. Okay, so that's the you can use CH, CH2, CH3, and then a CH3 over here, and then here is your Br or chloride, whichever halogen you want to use, but this is your alkyl halide. Okay, that will give you this product. So this is also a Williamson's ether synthesis. The next reaction is a Grignard's reaction. So first step is formation of the Grignard, and then reaction of the Grignard with a aldehyde, followed by protonation. So that should give you a product of this type. Right, so I have the CH3CH2 here, that's the CH3CH2, then I have the hydrogen, which is this one, and then this oxygen turns into the alcohol group. Okay, so if you highlight where is the attack happening, this is the carbon onto which the Grignard reagent attacks, so that is this carbon here. Okay, and then we have the CH2CH3, which is this one. The next one is also a Williamson synthesis. Looks like this review has covered quite a few of that. So reaction with a simple alkyl halide and then we have the CH2 already in here, your oxygen, right, and then the CH3. The last one in this page is our reaction or ring opening reaction of a ether. Okay, so you have to write down the it's an acidic cleavage of ether. That is the reaction here, and we can draw this as CH3. This is the same compound, CH, but now we had it as the ether, right? O CH3, correct? And then here is where my CH3 is, the second CH3. So 1, 2, so that's the 2 CH3s, and then I had the OH here, but that is the one that cleaves here, right, with the acidic cleavage, and so you get back the alcohol and the alkyl halide. Okay, all right. So those were the reactions of alcohols. Oh, there are some more here. We have a alcohol with POCl3. That's a formation of an alkene. So it forms the alkene, then E2 type of reaction. Okay, so it's an E2 elimination reaction, where the major product is the alkene, and water will be removed. Okay. Then the last one is your reaction with the epoxides. Again, the cleavage or ring opening reaction, acid, presence of an acid. So here, if you look, we have 2 carbon atoms, right? One is a primary and the other is a secondary. Okay, so in this case, the chloride, when you have a choice between primary and secondary, the chloride will attack the primary. Okay, so here is where it will attack. So first step is the protonation. Okay, so we will have a protonated ether first, then this will attack, and this goes over here, right? So we have the C. So if you number this, okay, let's number this one. 1, 2, 3. Okay, so on 1 we don't have anything. On 2 we will have the alcohol, right? And 3 we will have the chlorine. Okay, so this is how you have to get the product. Okay, so between a primary and a secondary, the chloride will prefer the primary, but if it was between the tertiary and the primary, it will prefer the tertiary. Okay, all right. Moving on to the next question. Outline a synthetic step to carry out the conversion below. So here we have a benzene and it's forming the alcohol. So looks like Grignard's pathway would be the best one. So we have a benzene. The first step to form the Grignard, so you will have to do the Br2 FeBr3, which will form the bromobenzene, react it with magnesium and ether, and that should give you the Grignard's reagent, MgBr. Once you have the Grignard's reagent, you can use the appropriate carbonyl. Now, in this case, you are using a ketone of this type, right? Because you have a cyclohexyl type of group, so that's the ketone you will use, followed by hydrolysis H3O+, where you can get your required target material. Okay. The next one, you have to use the correct Grignard and carbonyl compound to form the product here. So here you have 2 pathways which you can use. One is the C6H5 MgBr, right? This Grignard, and the carbonyl can be this one, or you can use this carbonyl benzaldehyde and react it with CH3, CH2. Okay. The next one is to provide the structure of the final product here. If you look, it's an alcohol and you're treating it with PBr3. So your product A should be CH3, CH2, CH, CH3, and Br. Okay, that means you're just replacing this OH with a Br. So that's A. Then you're treating it with magnesium and ether, so obviously that's going to make a Grignard's reagent, which will be CH3, CH2, CH. CH3 is still there attached, and then you have the MgBr. Magnesium gets inserted between the carbon and the bromine. And then C will be the alcohol now. If you're treating it with the aldehyde here. And finally, C will be the oxygen with a negative charge, right? Alkoxide type of group, and then finally protonation to give the alcohol. Okay, so we can draw the structure of C. Here the question is asking only the final product, but you can show in each one of them. So that's the carbon, this one. We'll have the CH2, CH3. Hydrogen. Charge. Sorry, this one has CH3. Special CH3. Right, I'm just redrawing this one, and then that's here is where your attack by the Grignards happens. So the carbon, this carbon is here. That's this carbon here, and then we have a CH2 CH3, then a CH3. Right? So maybe we can put the color here in order to show. So this carbon here, the red carbon, that's this one. Okay. And then we have the CH3 attached to this, and CH2 CH3, and then maybe the color to the carbonyls carbon, which is this one. Okay, and that carbonyls carbon is carbonyls carbon. Okay. So we still have to protonate this. That's what the D step is. So D will give you the final alcohol, which is OH, H, you have the carbon, which goes like this, hydrogen, right? So that's your final product D. Okay, so basically you have 1, 2, 3, 4, 5. It's a secondary alcohol, that's right. Okay. Next one is how will you distinguish the following using NMR? So the first one will have one single peak, right? Because they are all similar, and well, you may see a tiny peak for the hydrogen if it is a pure compound. So you may, but mostly you might just see one single peak because all of these CH3s are equivalent. Okay. For the next one, you will see a septet for this one, these two. Okay. These two will provide a septet, and then this will have a doublet. Sorry, let's label them as A and B. AA, and then this one is B. So B will actually be the septet, and A will be the doublet. Okay, and then for CH2, this one, they see only one neighbor. Oh, sorry, let me step back and do this one more time. Okay. So this proton here has how many? 3 plus 3, 6, 7, 8 neighbors. So this should appear as a nonet, right? Now this has got only one neighbor, so this should appear as a doublet. And then same thing with this, these two, they will also appear as a doublet. Now for this ether, you will see a quartet triplet pattern because of the, you can call this as A, then B. A is a triplet, and then B is a quartet. And then the final reaction in this review was to predict the product of this one. If you look, we have a strong nucleophile, it's a ring opening up an epoxide. Okay, so we have a strong nucleophile. So this should result in where the first step would be 1 and 2, so your OH goes over here, then the nucleophilic OH comes and attaches on the other side. Okay? But you have the oxide in the final step where you react it with water, so you get a diol. Okay, so let's again put some color here. So this oxygen is this one, and then this one is your oxygen coming from the sodium hydroxide. Okay, so basically this goes and attacks here. This opening it up, so that's why you have an oxide here. And then the final step is to protonate it, and you get the alcohol. Okay, so that was the answers for this review. We'll do the next review in the next video.